In this video, we are going to look at a practical application of group theory. We will see that hidden under a simple real-life example is the intricate workings of Burnside's lemma from group theory. At the end of this video, you will hopefully have picked up a few key concepts of group theory, allowing you to recognize and understand Burnside's lemma. Before looking at group theory, let's take a trip to the local necklace store. This store only sells necklaces that consist of 5 beads, and what makes this shop unique is that no 2 necklaces sold are the same. Furthermore, this shop has a container with lots of beads. In total, there are n different colors a bead can have. We can think of our necklace as a pentagon with a bead on each corner. We then number the beads 1 to 5. For each spot, we can choose from n colors. Take, for example, n equals 2, or in other words, 2 different colors for the beads. Here is an example of a necklace that would be sold in the shop. The store owner asks you an interesting question. How many unique necklaces can the store sell, assuming you have an unlimited amount of beads at your disposal? We could try to solve this problem in the following way. We can place one of the n different colored beads on each spot. This gives a total of n to the 5 necklaces. But is this the answer to our problem? Unfortunately, it's not that simple. Consider these 2 necklaces labeled A and B. Although they have the colors at different beads, we could rotate one of the necklaces, namely A, to get the other. So these 2 are not unique, as they are the same necklace. Therefore, our answer n to the 5 is an overestimation, as it contains duplicates. Due to the fact that we can rotate our necklace, our original answer gives duplicates. This is related to the symmetries of the necklace. In this case, we are looking at the symmetries of a pentagon. For the moment, do not think about the coloring of the necklace, but only the fact that the necklace has the shape of a pentagon. The coloring is here to help you see the symmetry being performed. We will look at the symmetries that a pentagon has. Pentagons have rotational symmetry. This means you can rotate the pentagon and the shape stays the same. We can also flip the necklace to get the same shape. Now, let's look at a symmetry that linked necklace A with necklace B in the previous example. This is the symmetry of clockwise rotation by 72 degrees. We can also rotate by 2 times 72 degrees, which gives 144 degrees. And we see that this is also a symmetry of our pentagon, as is 216 and 288 degrees. So our necklace possesses 4 rotational symmetries, which preserve its shape. The second symmetry is the flipping of the necklace. We do this by drawing a line through the center of the necklace and a numbered bead. We then flip the necklace in this line. This symmetry is called mirror symmetry. There are 5 such lines, which have mirror symmetry. Technically speaking, doing nothing with the necklace is still doing something. We call the symmetry of doing nothing the identity. You can think of this also as rotating the necklace by 0 degrees. This is our final symmetry. If we count all the symmetries together, we see that the pentagon has 10 symmetries. We can also look at symmetries after one another. For example, first rotate this necklace 72 degrees, and then flip it along the line going through the top bead, or bead number 1, and the center. This is the same as flipping the original necklace along the line that goes through the center and the third bead. So we see that symmetries done after one another is the same as another symmetry of our pentagon. This leads us to the definition of a group for the pentagon, noted as D5. The group of the pentagon is the set of symmetries of the pentagon which contain the identity, 4 rotations, and 5 mirror symmetries. A multiplication is defined on our set D5 as the symmetry achieved when performing 2 symmetries after one another. Note that a mirror symmetry after a rotation of 72 degrees is not the same as a rotation symmetry of 72 degrees after a mirror symmetry. A key property of groups is that there is an element that does nothing, our identity element, and each element has an inverse. For example, the inverse of a 72 degree rotation is a 288 degree rotation. Now that we have defined a group, we move on to group actions. We use the symmetries of the necklace to act on the colored necklace. For example, a rotation symmetry from D5 can be used on the necklace, which is like physically rotating the necklace. It is important to also be aware of the colors of the necklace now. Specifically for this problem, we define a term called the picture of a necklace. A picture of a necklace is a necklace which we cannot act upon. Take, for example, the necklaces A and B we saw earlier. They are the same necklace, but they are different pictures. In the beginning of this video, when we estimated the number of unique necklaces to be n to the 5, this is actually the number of unique pictures. If one takes a necklace, the set of all pictures we can make by acting on the necklace is called the orbit of a necklace. Using our 10 symmetries acting on the necklace, we can find all such pictures in the orbit. For example, take this necklace. We apply all symmetries on this necklace and get the orbit. Now, what would you expect the orbit of this necklace to be? Note that this necklace was in the orbit of our previous necklace. Take a moment to pause the video and think about this. The answer is that the same orbit would be obtained. A very important fact for a problem is that any 2 necklaces in the same orbit may be different pictures but are the same necklace. We now have enough tools to start solving our problem. Our goal is to find the number of unique necklaces. We will do this by trying to count the number of pictures all the orbits of these unique necklaces produce. We first suppose that each unique necklace produces 10 unique pictures in its orbit. Since we know that the total amount of unique pictures is n to the 5, we would have that 10 times the number of unique necklaces is n to the 5. Now let's check if this works by considering 3 different types of unique necklaces. Necklaces with no symmetry, mirror symmetry, and rotational symmetry. We first consider orbits of necklaces with no symmetry. The orbit of this necklace has 10 unique pictures. This so far supports our original guess. Now let's consider a necklace with mirror symmetry. A necklace with mirror symmetry can have the choice of 3 colors. Thus, there are n-cubed necklaces with mirror symmetry along the vertical axis. The first thing to note is that in the orbit of a mirror symmetric necklace, is that its orbit produces all the rotations of the mirror symmetric necklace. Secondly, and most importantly, we see that there are only 5 unique pictures, as some pictures produced in the orbit are the same as others. So, the orbit of a mirror symmetric necklace only has 5 elements instead of 10. What does this mean? This means that in our original estimate, we overcounted the number of pictures produced. So we must add on the duplicate pictures, 5n cubed in total, to our answer for it to be correct. So we now have 10 times the number of unique necklaces is n to the 5 plus 5n cubed. Now let's check the rotationally symmetric necklaces. A necklace with rotational symmetry can only have one choice for the color on all beads, as each bead goes to the next one. Therefore, there are n necklaces with rotational symmetry. It is important to note that a rotationally symmetric necklace is also mirror symmetric. The orbit of such a necklace gives only one unique coloring, but we have that 5 of the duplicate pictures are produced by mirror symmetries, and 4 of the duplicate pictures are produced by only rotations. So, we have still overcounted the number of pictures produced, because for rotationally symmetric necklaces, there is only one unique picture produced. Therefore, we must add 4n duplicate pictures to our answer. So we finally have that 10 times the number of unique necklaces is n to the 5 plus 5n cubed plus 4n. We see that necklaces with symmetry are the ones where the orbits contain less pictures, but we have gone through all possible symmetries. Thus, the number of unique necklaces is n to the 5 plus 5n cubed plus 4n all over 10. We have now found a formula for the amount of unique 5 beaded necklaces which can be made out of n colors. Suppose that we have 3 colors, so n is 3. Then we plug this in and see that there are only 30 unique necklaces possible. The underlying math behind this formula is strongly related to group algebra, which studies the idea of symmetries. A formula, known as Burnside's lemma, gives the number of orbits an object with symmetries has. Loosely said, the formula states that the number of unique objects multiplied by the number of symmetries of that object is equal to the sum over all symmetries of the object of the number of pictures that remain the same under that symmetry. This way of calculating the number of unique orbits is much faster because we do not have to go through the overcounting argument that we used in this video. For example, we had the group D5, which had 10 group elements. We saw that there are n to the 5 pictures that remain the same under the identity element. There are n cubed mirror symmetric pictures for the vertical axis, and we have 5 mirroring lines which we can flip pictures about. And for the 4 rotations, there are n pictures that are conserved under the rotation. So, applying the lemma gives the same answer as before, namely n to the 5 plus 5n cubed plus 4n all divided by 10. You now return to the shop owner, satisfied with your answer. The shop owner now decides to expand the business. The shop owner asks you the same problem, but for a necklace with 6 beads. Can you solve it?